So hello everyone, welcome back to our graduate seminar organized by the UOV Geotechnical Center. My name is Lan, and in today's seminar we will have a special presentation given by Dr. Lukas Arenson on the topic of Introduction to Permafrost Engineering. Before he presents, it is my great pleasure to give a short introduction of Lukas. Lukas is a Principal Geotechnical Engineer with 18 years of expertise in permafrost engineering, especially in frozen soil mechanics, periglacial risk assessments, and geothermal modeling. He received his PhD in civil engineering at ETH Zurich, Switzerland. He has worked on infrastructure and mining projects in Arctic and mountain permafrost, and on the stability of frozen slopes in the European Alps, the South African Andes, and Asia. He has been involved in consulting and the research work related to preventing permafrost degradation, re-establishing pre-construction thermal regimes after constructions. He has also studied effects of climate change on northern transportation infrastructure as part of various projects. Lukas teaches permafrost engineering courses at the universities and for industry, and published various scientific publications in the fields of frozen soil mechanics, permafrost engineering, rock glaciers, and glaciology. He is also an editorial board member of the Canadian Geotechnical Journal and was associate editor of Permafrost and Periglacial Processes, and on the editorial board of Cold Regions Science and Technology. He is currently president of the Canadian Permafrost Association and was chair of the Cold Regions Engineer Division of the Canadian Geotechnical Society. He is an Adjunct Professor at the CivilEngineering Department of the University of Manitoba. He was the recipient of a couple of prestigious awards from the Canadian Geotechnical Society for his contributions to permafrost engineering research and to the Cold Regions Engineering Division. So with such a long list of introduction, now I'd like to invite Lukas to this virtual stage, and we are looking forward to your presentation on this interesting topic. Now the floor is yours, Lukas.
Thank you very much for this kind introduction. I need to create a shorter version. Okay, so I hope you can see my slides, my presentation, and as the title said, it's an introduction to permafrost engineering, and it's probably a lot of material that I'm going to throw at you. But the idea is to give you a little bit of an overview of what is important when it comes to working in the north and in permafrost environment. So just very briefly, you've heard already a lengthy introduction, so I'll skip this slide. Just want to give you my background here, what wasn't mentioned. So I'm originally from Switzerland, and that explains the accent that I have. So let's jump right into it. Cold regions engineering. So what is different from working in a permafrost environment versus non-permafrost? So first of all, we often have to deal with ice, with ground ice. And ground ice's mechanical behavior is highly non-linear. You may be familiar from glaciers, and you know that glaciers creep, and that's one of the aspects we have to deal with. And the temperatures, or sorry, the ground ice is temperature and time dependent. So the warmer it gets, the softer it is. And it is, in essence, a viscous material. So there's no long-term strength to it. So it depends on the time. If in short term, ice can be very strong, it's brittle, so you can stand on it. But eventually, if you're building something on ice, it will creep and deform away. So there's this time component. Third important aspect is climate change. And when we talk about the Arctic, climate change is impacting northern areas, specifically Arctic and polar regions, much more. So we talk about 3 to 4 times the global average when it comes to warming. So in other words, we're dealing with a material that is temperature dependent in an environment that is rapidly warming. So that's definitely a challenging aspect. And because of that, we can no longer simply look back and think of what happened in the past and extrapolate it to the future. So when we're designing, we have to find ways of anticipating how our foundation, for example, is changing over time, or how some of the geohazards that we have to deal with may change because a certain hazard may not have happened in the past because the environment was frozen. So these are the four fundamental aspects that cold regions engineering makes so fascinating, but also complex. Now, what does that actually mean, and what is permafrost? So I just pull up here the definition, the original definition that was coined by Muller in 1947. And when we talk about permafrost, we mean soil or rock with or without included water that has remained at or below 0 degrees centigrade for 2 or more years. So when we talk about permafrost, we have two components. One is the temperature component, and the other one is the time component. But it's not a state. So permafrost is not a type of a soil, and it also doesn't tell you whether there's ground ice in it or not, because permafrost, by definition, does not talk about the state of the material. So you can have ice-rich material, and you can have ice-poor or even dry permafrost conditions, so there may not be any moisture in it. Both is permafrost. So only because someone says there's permafrost or you're working in a permafrost environment, that doesn't give you the full answer in terms of what foundation might be suited for a certain area. Now, this is, for me, the most important graph when it comes to permafrost. If you understand this graph, you understand 99% of importance that, or what is important for permafrost. So what is this graph? It's called a trumpet curve. And what it gives you is the temperature range at depth. So let's assume you have a borehole, you throw in a thermistor, and you measure ground temperatures for the full year. Close to the surface, you have very cold minimum temperatures during the winter and warm temperatures during the summer. As you go deeper, this amplitude narrows. And this is what you can see with this trumpet curve. And at some point, which we call the depth of zero annual amplitude, the temperatures remain constant. And as you go deeper into the ground, temperatures warming. So the center of the Earth is much warmer than the surface. So that's why we have this gradient that it gets warmer. So now that you have this curve, we have the ability to define what is our permafrost. So even in the very high Arctic, the temperatures close to the surface are getting above 0 degrees. So this top layer can actually thaw in the summer. And if you recall the definition of permafrost, where it needs to be at or below 0 degrees for 2 consecutive years, the top is not permafrost. This is called the active layer because it seasonally thaws. And then where this maximum line crosses the 0 degree, that's the permafrost table. So that is the top of the permafrost. And if you go now deeper, the ground there stays at 0 degree consecutively for at least 2 years or even longer. So that's what defines the active layer and then the permafrost table. Now we have permafrost until you reach a depth at which ground temperatures are above 0 degrees again. And that's your permafrost thickness. So permafrost is not going to the center of the Earth. So there's a limit. And this could be a couple of meters or can be a couple of hundreds meters, and we'll get to that. Now, from an engineering perspective, you can imagine the most challenging part is actually this active layer. So where we have frozen condition and unfrozen condition, and that vary. If it just remains frozen, that's much easier to design for than that constant variation and frozen conditions below. Where can we find it? So it underlies about 50% of the Canadian landmass. And we typically differentiate between two distinct zones. One is called the continuous zones, where it can be up to 500 meters thick. And then you go further south, the discontinuous zone, which is also separated in some other subcategories. It can be found in the north, where it's cold, but also at high elevation. So if you go higher in elevation where it's getting cold, you're reaching permafrost, and that's now called mountain permafrost. I was talking about the active layer, which is the upper part of the soil that thaws annually. And it can be thin, as I say here in the high Arctic, maybe a couple of centimeters, 30 or 30 centimeters, until you get several meters if you go further south. And then there is this layer, which is called the permafrost table, which is the base of the active layer and the top of the permafrost. There's also a phenomenon called the talic. And the talic is an unfrozen body within the permafrost environment. And it's typically caused by flowing water. So if you have water that can transport heat, you may create these talics, or under a lake, you can have a talic, or under a river, and that affects your foundation, but it also affects hydrology. So a very important topic that needs to be understood. Now, how old is permafrost? Very old is the short answer. And you may have heard of animals that were actually found. And here is a famous mammoth that was found in the 70s, and it was dated to 40,000 years back. And more recently, actually, there was this wolf puppy that was found in a placer mine in the Yukon. It was found in 2016, but only last year was actually revealed to the public, Zurich. And this particular puppy, very well preserved, was dated to 57,000 years old. So we know from these founds that some areas permafrost was tens of thousands of years old. This is the circumpolar distribution of permafrost. So we're looking here from the North Pole. We got Canada, so North America is here on your right. On the left, you got Russia. To the north is Europe, so it's a little bit of a different world on the planet. And we can see this purple, that's what we call continuous permafrost, where about 90 to 100% of the area is covered by permafrost. And then as you go further south, that's when the ground is warming, and that's where you have less permafrost, from discontinuous to sporadic to isolated. So all these three are in essence parts of the discontinuous permafrost zone. And you see also some mountainous ranges. So we see here the Rockies, where we can find permafrost because of elevation. And because of elevation in China, this is the Tibetan Plateau, which is a high altitude plateau. But again, there it's not because of polar condition, but it's because of the elevation that you actually can find permafrost. If we just focus on Canada, then we note here a western to an eastern trend. So the Western Arctic is warmer than the Eastern Arctic, and that's because of how some of the air movements happen and how the Arctic and the oceans are influencing the temperatures and the large atmospheric streams. So you can't just say you have a certain latitude and you go whether east or west that you have permafrost. You don't have. So it's really driven by how these large air movements happen. And that's why the Eastern Arctic in Canada is colder compared to the Western Arctic. But you also do see here the mountain ranges, the Rockies, but also coastal mountains where we can find permafrost up at elevation. Now, Brian O'Neill in his 2019 paper now presented this ground ice distribution. So permafrost, as we learned, it's just temperature. But when we then look now at ground ice, that is different. And while this is a very high level map, it still does show where you have much more ground ice. So again, here, the eastern Arctic has a little bit less, or when we go into the Yukon compared to some of the Northwest Territories, Nunavut versus Northwest Territories and Yukon, and the McKinsey Delta, where we have much higher ground ice content. However, this is a very high level overview, and locally ground ice distribution can be very variable. And when it comes to engineering and foundation, you must have your local site investigation to understand where permafrost is and where it isn't. I briefly introduced that the thickness can vary from a couple of meters to several hundred meters. Here are some examples. If we go into Northwest Territories, Hay River, which is really the isolated area of permafrost, is continuous permafrost. So we may have permafrost, or if there is, probably sitting at 0 degrees and maybe 10, 12 meters. But the deepest known and measured is probably Raglan in the mine, where there's up to 500 meters of permafrost. So it's quite a range of where we can have permafrost and where not. And if we were to cut, let's say, a cross section from north to south, then that's typically how it looks like. So again, continuous permafrost, several hundred meters, thin active layer, and you may have these talics that I was talking about from rivers, lakes. They can be open, they're connected to the surface, or they may be closed, like entrapped in sometimes still kind of historic remnants. And then as we go further south, we're going to the discontinuous zone, and now there's a couple of breakthroughs, and we have some patches of permafrost as we go into the sporadic permafrost terrain, and we're actually going to get much thicker active layers as well. So depending on where you are, you're really going from permafrost everywhere to hardly any permafrost that you can find. So you need to really understand where you are from a geographic location, and then where your permafrost, and then within that permafrost, where your ground ice may be, if you have to design your infrastructure, which is probably more challenging if you have a linear infrastructure. And we'll get to that later in this presentation. Now, we talked briefly about climate change, and here is a projection of how the permafrost environment may change in the future. Now, permafrost, because of the ground ice and the latent heat associated with ground ice, is actually reacting very slowly to climate change. So you can't just assume air temperatures are increasing and ground temperatures would follow suit at the same rate. That is not the case. Actually, ground temperatures are warming at a much lower rate. However, we're seeing near surface changes, right? And they're developing in terms of thicker active layers, or what this map shows, more talics. So those places where permafrost will disappear, but only locally, those places increase dramatically as we go through global warming and as we see it. And for our designs as engineers, that is what makes it challenging. So it's not a uniform degradation and thawing of the permafrost, but it's a complex thickening of active layer and increase of those talics, which are these areas where permafrost disappears within a general permafrost environment. Now, if we go into the mountain regions, where I was indicating that permafrost exists because of elevation, we have another level of complexity, and that is the solar radiations. A lot of permafrost and ground surface temperatures are impacted by solar radiation. So when you have a north-facing slopes, for example, you get less sunlight compared to a south-facing slope. So north-facing slopes are typically colder than the south-facing slopes, which means that at the same elevation, you may get permafrost at lower elevation. You get thicker permafrost, at the same elevation on a north-facing slope versus a south-facing slope. Or if you go to lower elevations, there may be no permafrost on a south-facing slope compared to a north-facing slope where permafrost may still be present. So there, topography and how different sides of your mountain ranges are protected from sunlight impacts where permafrost may or may not be. So it's worth looking at solar radiation maps if you need to understand where permafrost may be within a mountainous environment. So that's different from polar regions where it's really the latitudes that dictates a lot and air mass movements where permafrost may be or may not be. Just another typical cross-section through some of the permafrost, similar to what I've shown earlier, but several hundred meters here in the north. And as you go further south, you're going into discontinuous permafrost with a couple of meters left, a couple of meters of thickness of the active layer versus centimeters, tens of centimeters in the high Arctic. And as we've seen in this map from climate change, so what we're expecting is that these zones here, these are widening. It's not that all the permafrost disappears due to climate change, but we're going to get much more complex forms of this discontinuous permafrost zones, thickening of the active layer, and so on. So if we're switching to the Arctic permafrost areas, so there's a typical example of how the high Arctic looks in the summer. One of the key phenomena are these ice wedges. So it may look nice and green and uniform from the top, but when you start digging in, you see what we call ice wedges. And those ice wedges can be several meter wide, but also here for scale or two people, they can be tens of meters deep. Why do we know they're ice wedges? Sometimes we see these polygons. So wherever you have one of those polygons, that's where an ice wedge may be underneath. How do they form? So if you assume you have uniform conditions, just flat and uniform. Now, when it's cold, the material or the ground wants to contract. So like all materials, they're trying to contract. So the soil or the surface contracts, and because it can't contract the whole area, it starts to crack. And in nature, one of the ideal conditions to contract is these polygons, these hexagons that form. Sometimes they're squares, but the ideal case would be a hexagon. And so now you have this hexagonal structure with little cracks, and water can infiltrate. And because we're in a permafrost environment, so this water that now infiltrated starts to freeze. And as water freezes, it expands and it just creates a tiny little ice vein. But if you repeat this process tens of thousands of times, then that's when you end up having these ice wedges that form, and you can actually cut through the ice and you see that the ice is perfectly vertical because there was a little crack, water infiltrated, froze, and created another layer of ice. Now, even if we build infrastructure, we often then can see that because there's still some movements going on. And if it is warming, then the ice actually does start to thaw and creates these little gullies. So we can see these hexagonal or polygonal structure in very aspects around this environment. Another typical phenomenon, more in if we have topography, is solifluction. So this is when the surface, the active layer in essence, start to creep a little bit every year on top of the permafrost. And the creeping is not the perfect, or is not the correct term, because in essence, it is a heaving process and a settlement. And the reason why it starts to show these lobated features is heave is going to be perpendicular to the slope, but the settlement happened vertically. So every year the slope is heaving and settling. So it's doing a little bit of a zigzagging deformation down. And if you add up millimeters per year, or maybe centimeters, but typically very small, if you add that up, end up with these type of slope. It's a good indicator that permafrost is around, and it's also a good indicator that this whole slope is slowly moving. So if you have your road or your pipeline, or even any other type of foundation, that may be a challenge. Another phenomenon is that we can create liquefaction conditions because of the permafrost. So here's an example where we actually did a little bit of drilling in the high Arctic. And because of the disturbance that was done, we thought the ground ice that was present at the top of the permafrost and the water that was generated couldn't drain. You have an impermeable permafrost layer at the bottom, and you have a very thick vegetation cover at the surface. So suddenly your water is trapped between the permafrost and the vegetation layer on top. And that can create undrained conditions, and that can cause obviously some challenges for your foundation. The last phenomenon I want to show are pingos. Pingos found in the high Arctic. Here's a famous pingo near Taktajaktak. And pingos are mountains that grow as ice starts to accumulate within it. Typically, they start to form within a talus. So there is unfrozen material and water available. And over time, again, we're talking thousands, 10,000 of years, ice lines after ice lines start to form near the surface and just pushing the mountain up a little bit and a little bit. So these are, if you wish, like blisters filled with ice. So if we were to cut through it, there's a lot of ground ice in these features. So when you see any form like this, you know there's a lot of ground ice in it. Now, if we go further south, going from the high Arctic to the southern limit of permafrost, permafrost remains in areas that are thermally protected, and typically like peat plateau are good indicators that permafrost may still be under there, whereas where you have moss and peat and water, that's where permafrost has gone. And that's when in these forested areas, you'll see a lot of these trees tipping in all different directions. And that's a good indication that the permafrost is degrading or thawing in these water bodies, being it a river, or being it a lake, being stagnant or not. And so you have them tipping in all different directions. That's why we call them trunken trees. So it's not like a mass movement or a slope where slowly all trees were to deform in the same direction. They were all bent into the same direction. They tip in all different directions. And that's a good indicator that permafrost and ground ice is still in there. Another phenomenon that we can see are thermokarst lakes. So thermokarst is when ground ice thaws, and often we see these more rounded lakes to form. So that's a good indicator as well that these lakes and this area must have had, or maybe still is, underlain by ground ice and massive ground ice that thawed over time, left a landscape like this. So when you were to build something, you need to make sure that you understand, is there still ground ice there or maybe not? We often also find more recently a lot of mass wasting, specifically through retrogressive thaw. When permafrost starts to thaw, it's very difficult to stop it from keep thawing. So we see these phenomena starting maybe at a riverbank or a lake, and then over time, more and more of the area start to thaw and just retrogressively going back and typically increasing in size. Here is a video that shows some of this phenomenon forming, and you can see that just the permafrost and the ground ice that is exposed here starts to thaw, and there's a lot of water that allows then the material just to drain and flow away in essence. And it's nearly impossible to stop one of those retrogressive thaw slumps if they have started. And they can have significant sizes. So here's an example from the Northwest Territories Geological Survey, did this drone video. And once they start, they also have a major impact on sediment transport or whatever material, or if you have a road or a pipeline or even buildings downstream of such retrogressive thaw slumps, they can have a significant impact at large distances downstream of where the actual thawing front is occurring. You may have also heard of those mega slumps that can be found in Siberia. So it's a slightly different process, but it's still major thawing of ice-rich permafrost. In this case, we'll talk about 800-meter width of this mega slump that is occurring and slowly developing in the Arctic. You may have also read of these methane craters, again, specifically in the Russian Arctic. I'm not aware, I haven't read of anyone in North America, but what happens there is that methane starts to accumulate at depth. And it's believed that because the permafrost is getting warmer and slightly less stable, plus the pressure within the methane gas that it's producing is increasing, then suddenly those craters start to blow out. And in this particular case, there is a 25-meter hole that was actually generated from one of these methane craters. And again, if you think about permafrost infrastructure or infrastructure in the area, if you have road, railway, pipeline in the area, you want to make sure that those craters do not blow out close to your infrastructure. Finally, another phenomenon are frozen debris lobes. They can be found in the Brooks Range in Alaska. And this is, in essence, ice-rich permafrost that is slowly creeping downslope. Now, slowly, we're talking centimeters, maybe meters per year. And again, if one wall of frozen debris is coming towards your road, in this case, that's the Dalton Highway, a lifeline for the North Shore and for the oil and gas industry of Alaska. If this piece of infrastructure is impacted by this frozen debris, that has obviously significant economic consequences. Lake outbursts is another phenomenon that's been observed, and it's just an additional consequence of these retrogressive thaw slumps. So you see here material failing in a retrogressive way, and this lake then drained eventually, and in the Northwest Territories, and it was provided by the Northwest Territories Geological Survey, this picture. So if this moves further away, further up slope, then at some point this dam, this natural frozen dam, starts to breach, causing an outburst flood. And if you have infrastructure anywhere close downstream, this can cause some different challenges to that particular piece of infrastructure. So understanding these phenomena is important because it also dictates how you want to do your site investigation. So we learned that it's not only the temperature that needs to be understood, but the ground ice. So when you do site investigations, it's important to find the ground ice and characterize the ground ice. So whenever you plan a geotechnical investigation program, it's the presence of the ice, the characteristics of the ice. Also, the salinity. So if you have, specifically in coastal environments, if you have saline conditions, that impacts the freezing point of your material. So you might be at minus 0.5 degrees, but your material may still be unfrozen, even though you're in permafrost, or so-called cryopec, but because of the salinity, you have a freezing point depression, and you do have unfrozen condition. So your foundation is on unfrozen ground, even though you are in permafrost. And finally, climate change. So you want to understand how climate change may impact your foundation, for example, in the future. So when you get those data, it's often you need some baseline data, and you can only get them from monitoring. So you want to understand, again, your ground temperatures. You want to understand how some hazards have changed, so some deformation. So we talked about these solifluction or these frozen debris lobes, retrogressive thaw slumps. So you want to understand how those processes change right now, but how they may also change in the future. Hydrology, what is your runoff? What does your flow in a certain watershed looks like? So all those aspects are important because you need this information for your design, understanding your hazards, understanding how your infrastructure impacts that behavior. So you want to for performance control. And if you are, for example, in a mining environment where you need to close your project, you also want to have that baseline data for your closure design, and you want to have those early on. We talked about that it's a thermal condition permafrost. So we need to understand where is the ground ice, because often you do not see it from the surface. You can only infer. So indirect measures are very good to infer where permafrost and ground ice could be, but it's not complete. So when we look at it overall, so we can look at the landscape, we can look at the dynamics. Climate is going to tell us. Ground surface temperature is also telling us something about the temperatures at depth. Geophysics, very useful tools, but it's always an indirect method. And modeling such as a permafrost distribution, ground ice distribution, thermal modeling, and so on. Because it's really only when you stick in a thermistor at depth, measuring the ground temperatures for 2 years, when you really know there's permafrost or there's not. Test pits, boreholes with good samples. That also is important to understand what is the characteristic of your ground. Indirect methods have a lot of advantages. They're relatively inexpensive. You can cover large areas, but you also want to make sure that you validate those. But again, there's been lots of improvements in the technology, from being at the accuracy, being at the spatial resolution. Take INSAR, for example, very useful tool, or some of the geophysics. But you want to understand and you want to calibrate them against actual measurements, because they're indirect and they will never going to tell you 100% with 100% certainty what you have, and they're never going to tell you the ground ice that you're going to have. So direct methods are really the only way to confirm that there's a permafrost. And specifically when it comes to how much ground ice is there. The downside, They're expensive, specifically when you are in a remote location and you need to core, and you need time, and you need, or you only have the information very locally, so you can't drill everything. And as we've seen, ground ice can vary significantly. So it's this extrapolation requires an understanding of your local conditions. So these are just an example of a very small drill rig, but it gives you interesting and very useful information here, for example, about the ground ice at depth. You want to understand your sample, and you can see how variable the ground can be with massive ice versus just frozen ground. But you want to understand your samples on site. And when you remember back with these ice wedges, it is very critical to understand where you drill and how this landscape is formed. So here's just a cross section through some of these, what we call Jedama, ice ridge versus, so wedge ice versus no ice. And that's how it looks in nature. So if we go back to the schematic, sometimes if you do not have these cuts, you do not know whether you drill here within just the Jedama, which is ice poor, or you actually drill within an ice wedge, and you could be 20 meters off, and sometimes you do not see at the surface where this ice wedge may be. So understanding your overall landscape, understanding how the permafrost may have gotten there, how the ground ice may have formed, helps you when you then have your point data. Maybe you complement that with your physics to get the full picture. So it's important to actually plan properly, use the different techniques, use these different puzzle pieces to combine them. And it takes time, so it's worth really investing in the time to prep your site investigation, because that really helps you over time with your design. Now, I know it's a lot of material, but I just still want to jump into a little bit of infrastructure and how we deal with certain infrastructure within the Arctic. So here's a couple of examples what we can do. So we can build, so this is an example from Russia. You can build large buildings within a permafrost environment. Typically, you use pile foundations, and they also have all an air gap allowing cooling of the ground so that the permafrost is not warming quite significantly under the building. You can also use something called thermosiphon that are either passively or actively helping to keep the foundation frozen. Another key component is when you build infrastructure in permafrost, you want to build up and not down. So you do not want to dig into the permafrost. So you always want to build embankments, as you can see here on this picture, but also on the right. And with the Trans-Alaska Pipeline, you also see it was built above ground to minimize thermal disturbance. And construction, if you build in the winter, that's also an advantage because it minimizes the disturbance of the environment as you build your infrastructure, for example. Now, what happens if you run into thawing? The thawing typically doesn't happen equally. So very frequently we have these thawing along embankment, for example, that results in the spreading of the infrastructure and these longitudinal cracks. Or if you're crossing from ice rich to ice poor conditions, you can have deformations along your alignment. Can be even more catastrophic. For example, if you have these ice wedges, if you have a large ice wedge that thaws, your infrastructure may still bridge it up to a certain point, but can potentially create a sinkhole and fail catastrophically. And coastal erosion, where we can have permafrost slowly being degraded over time due to the impact of waves and warmer temperatures. I was mentioning thermosiphons. They're very efficient in cooling the ground. In essence, what they're doing, it's compressed CO2 nowadays. And when CO2 is exposed here to the cold, so you imagine it's winter, air temperatures are cold, the CO2 liquefies or condenses, and then it creates a droplet that falls down into the ground. And if the ground is warmer than the air and the evaporation point of the CO2, then the CO2 evaporates, gets into a gas phase, and slowly moves again up to the top of these thermosiphons. And this is a circle that just continues as long as it's cold outside. And by that, you're extracting more heat out of the foundation, keeping the foundation colder in the winter, so that during the summer, when nothing happens, but just the ground is warming naturally, you have enough cold in the ground to survive another summer. So that's how you generate this artificially cooled permafrost conditions. And they can be used under embankments or under buildings, or, for example, foundation for the Trans-Alaska Pipeline, where you see lots of thermal piles along this infrastructure, keeping the piles that would otherwise impact the foundation frozen and solid. And also use them under buildings to increase the strength of the piles that are founded in permafrost. So it's the same concept. So again, it's been a lot of stuff, so I'm just gonna summarize it in a couple of take-home messages. So the geotechnical design, and if we want to assess hazard associated with it, is challenging. You need to understand your permafrost environment, and you need to understand the processes and how they can potentially change. As we've seen from all those hazards, for example, the outburst flood, or retrogressive thaw slides, or solifluction processes. So it's important to expand our design environment and system. So it's not sufficient to just look at the narrow embankment or even within a thin corridor. We need to look outside and how this may impact our design in the future. Main concept is minimize thermal and mechanical disturbances. So that's why we build embankments up or build air gaps under a building, use thermosiphon to keep the foundation frozen. If you can minimize the disturbance, that helps you with your design. Use process-based assessment. So the past may no longer be representative for the future. So we need to understand how an environment may change. You may create more tailings due to climate change. That changes the hydrology. So you may see water flowing in a way it hasn't flown in the past because of the development of these tailings. And there are a lot of numerical tools available that should be used in order to improve our designs. And we cannot design for every potential scenario. I mean, there's so much uncertainties when it comes to climate change, from the modeling, and it starts with the fact which model to use or which scenarios to use, and then within which scenario, what model to use. So when we're designing, try to do adaptive design so that in the future, we can easily adapt to the conditions they may have occurred. And when it comes to climate change, use a systematic approach. So climate change is nothing but an additional hazard. So we need to understand what climate change may do. How does it impact your loads? How does it impact your resistance? And that's how you can then come back and try to do your adaptive design. So maybe there is a little bit of a paradigm shift that we need to do. In other words, we can no longer in this environment just say, okay, we build something and then we walk away to the next solution. No, we probably have to come back and maybe adapt our structure based on how the environment is changing, specifically in the high Arctic, where we have these rapid changes caused by climate change these days. And that wraps it up. Again, I know it's been a lot of material, and I hope it's not been an information overload. And I see there's been some questions there, and I'll try to answer them as well. So thank you very much.
All right, thank you so much, Lukas, for giving us this very enlightening presentation. You did a very good job in introducing some fundamental and important aspects of permafrost, and also lots of interesting designs and phenomena related to it. I really enjoy it. And yeah, so we'll have a Q&A at this moment. I do see some questions from the chat. And the first one regarding Alpine mountain permafrost, what is the lowest elevation is being observed? For example, on north-facing slopes. Do you have any comments on this?
Yes, I honestly cannot provide you with a quick answer. I need to get back to you what that exactly is. I mean, it's the lower elevation is it's increasing. So the further south you go, the lower there is this elevation. I'm a little bit hesitant in providing a specific elevation because we know there's some very localized areas where we can have actually permafrost at very low elevation. But I'll get back to you with some work that was I think Stuart Harris, he did some work back in the days, so I can get back to you on that one.
Okay, sounds great. So next one is about climate change, I guess. Given the historical climate data, how do you predict future air temperatures, they say in 50 to 100 years, considering global warming?
Yeah, so first from nomenclature, I'm trying not to use the term predict because I found that extremely challenging. So I defer to projections. And there, so when we do this design and we're trying to see what may be in the future, we're relying in essence on IPCC projections when it comes to air temperatures, or then the downscaled regional climate models that are prepared by PCAIC is, for example, an institution that's doing this. So we're relying on climate models, and depending on the infrastructure itself. So if you have a high risk infrastructure within a very sensitive areas, you want to make your own projections using different downscaling techniques that are really focusing on that specific areas. So yes, it does require some work, and it does require the inclusion of climatologists.
Okay, thank you, Lukas. Next one, for the methane craters, is that just spontaneous pressure release or like explosion you see in the Hollywood movie?
That's a good question, because nobody, as far as I know, has recorded any of those explosions, but they seem to happen very spontaneous. There's a paper that been published earlier this year, and so when they went back, they used INSAR to see how this explosion happened, and they saw there was a little bit of a heaving going on, but then the actual explosion happened quite dramatically. So it was very quick that the explosion happened, and then it was, so when they saw it and they went in there and managed to get some drone videos, because the crater itself filled rapidly with water again, and then they couldn't see it. So it was very interesting paper. And yes, they're probably quite dramatic, so they're rapid, but thanks to INSAR or measurement technologies, it's actually possible to maybe foresee where some of those happen, because you see a little bit of heaving first before it erupted.
Okay, thank you. Next question I have about the longitudinal cracks on the road of embankment. Are they likely on the north facing or south facing?
I'm not aware that there's really an orientation related. So typically what happens is that you have this spreading, and the spreading is caused by a thawing of the toes. So you have your embankment, I'm trying to show it here, and then you have the toes. And the thawing or the warming typically happens in the toe area. And often in the high Arctic, snow is the culprit. And snow is blown around in the high Arctic. So it's not, the Arctic is a desert, so there's not a lot of snowfall, but you still have a lot of wind distributed snow. And so on these embankments, you can have snow accumulating on one side, and snow is a good thermal insulator. So the areas that captures a lot of snow is typically the warmer side, and that's where you're thawing the permafrost more, and that's where the spreading happened. So I don't think it's necessary north, south, east, west facing. It's often driven actually by snow. Now, the melting of the snow is impacted whether it's north or south facing. So north facing areas keep the snow longer. But yeah, it's a very good question, and I haven't really looked into it.
All right, thank you, Lukas. And I think we do have the last question here in the chat. There was a PowerPoint slide with permafrost debris flow encroaching on an oil and gas road in Alaska. Is there a permanent stability solution for that scenario, or would continue rehabilitation need to be done to move the road over time to different locations?
That's exactly what happens there. So they realigned the road, and Margaret Darrow from the University of Fairbanks, what she did now is she actually used the existing road as a frozen debris lobe research site, and pressure cells were actually installed and thermistor, and with the hope of now measuring the pressure, and I think she has pore pressure sensors and temperatures, just to see what happens now that this frozen debris lobe impacts the old road. So, but the road had to be realigned because there's in essence no way of stopping this thing from coming.
All right, thank you. Actually, we do have another question coming up.
Yeah.
But we still have 2 minutes, so I think you can answer this one. What do we know and what we don't know about the highway embankment design and the foundation design in the Arctic? I note in our design, it can be very conservative, perhaps because of a lack of literature experience.
Yeah. I mean, the linear infrastructures is, quite frankly, the worst to build in the Arctic because your foundation is so heterogeneous, and the site investigation will never give you all the answers that you need. I mean, in essence, you need to excavate all the ground along the whole highway in order to understand what's underneath. So this will never going to be done. So that's why maybe we'll have to be a little conservative. Now, my approach would be that we just try to measure it, monitoring, and by that keeping the standard of the structure high. So understanding where you have these ice wedges, because again, you may not see all the ice wedges, but by using more modern technology, we're probably going to be better able of understanding how your highway reacts to the thawing of an ice wedge before a sinkhole starts and really creates a hazard for your road. So yeah, you're probably right. I mean, we've been building these roads for a long time, and there's still uncertainties when it comes to how the foundation behaves in there. So yeah, failure and malfunction still exists. So we just need to make sure to minimize it.
Okay, all right, that's all the questions we have here. Thank you again, Dr. Lukas Arenson, for this interesting presentation. And now it's good to wrap up the seminar. I really appreciate everyone joining this seminar, and for you also have a good session with us. with that, I will just conclude the seminar and have a good day, everyone. I will see you next time.
Sounds good. Yeah. Thanks, everybody.
Thank you, Lukas. Thank you, Lang. See you guys next time.
Fernanda.
Bye-bye.